Welcome to our Precalculus class for STEM students. Today's lesson is ellipse, definition, and its equation. Let's start the lesson with the definition of an ellipse. Ellipses are important curves used in the mathematical sciences. These curves arise most often in the areas of architectural and engineering drawings. Many roads, bridges, arches, stairs, windows, and vaulted ceilings are elliptical in design and need to be rendered accurately in technical drawings. Also, it is vitally important in astronomy as celestial objects in periodic orbits around other celestial objects all trace out ellipses. An ellipse is a set of points, x, y, in a plane, such that the sum of the distances of the point, x, y, from the two fixed points in the plane, is equal to a constant value. The two fixed points being referred to are called foci, plural form of focus. The definition can be best illustrated by analyzing this video clip. The two pins were set up so that they can represent the two fixed points, called foci, and the string will rotate around them. The path followed by the tip of the pencil represents the set of all points, forming the ellipse. Notice the lengths of the string from a point on the ellipse to one focus and to another focus. Their sum will always be the same from any point on the ellipse. Hence, the sum of the distances of the point from two fixed points is constant. An ellipse has two axes of symmetry. This horizontal axis of symmetry divides the ellipse into two symmetrical parts, the upper semi-ellipse and the lower semi-ellipse. While this vertical axis of symmetry divides the ellipse into semi-ellipses from the left and the right. The longer axis of symmetry is called the major axis. It is also referred to as the longest diameter in an ellipse. The shorter axis of symmetry is the minor axis. It is the shortest diameter in an ellipse. The end points of a major axis are called vertices, plural form of vertex. While the end points of the minor axis are called co-vertices. The 2 points that we mentioned earlier, when we define the ellipse, are called foci. Plural form of focus, since we have 2 of them. They always lie on the major axis. The center is the point on the intersection of the major and minor axes. Again, in ellipse, we have 3 sets of points: the vertices, the co-vertices, and the foci. Each pair of points are equidistant from the given center. The distance from one vertex to the center is denoted by A. The distance from one co-vertex to the center is denoted by B, while the distance from one focus to the center is denoted by C. One important property among these distances, A, B, and C, is that they represent the Pythagorean theorem. If we are to go back to the video clip earlier, and pause it right here, we can see that, if the center is in between the foci, the distance from this focus to this point on the ellipse, which is the vertex, is a plus c, while the distance from this focus to this point on the ellipse, which is the vertex, is a minus c. Hence, the sum of the two distances, a plus c, plus a minus c, is equal to 2a, are the length of the major axis. Since this length is constant, we can also say that these distances, q and r, has the sum 2a, where q and r are both equal to a. Therefore, we can imply that the distance from the vertex to center which is a, is equal to the distance from the focus to the co-vertex. Hence, it is equal to a if you will recall the concept of a right triangle. This a refers to the hypotenuse, or the longest side of the right triangle. By Pythagorean theorem, we can say that a squared is equal to b squared plus c squared. Another property of an ellipse is that it has two orientations, horizontal and vertical. The orientation will be based on the position of the major axis. If the major axis is horizontal, then the ellipse is horizontal as well. On the other hand, if the major axis is vertical, then the ellipse is also vertical. The equation of a horizontal ellipse, if its center is at the origin, or 0, 0 is x squared over a squared plus y squared over b squared equals 1. On the other hand, if its center is at hk, then its equation would be x minus h squared over a squared plus y minus k squared over b squared equals 1. Take note that, among the three pairs of points, the vertices and foci are collinear, lying on the major axis of the ellipse. The coordinate of the vertices are negative a, 0, and a, 0, since its length from the center is denoted by a units. The foci, whose distances are both denoted by c units, have coordinates negative c, 0, and c, 0. And the co-vertices, that lie on the minor axis, whose distances from the center is denoted by b units, have coordinates 0, b, and 0, negative b. Therefore, if we want to determine the coordinates of the points on the horizontal ellipse, we can just add and subtract to the x-coordinate of the center, by a units for vertices and c units for foci. For example, this graph, with a equals 5 units, by counting the distance from the center to one of the vertices, we can say that the coordinates of the vertices are negative 5, 0, and 5, 0. On the other hand, since the foci are both 4 units away from the center, we can just add and subtract 4 to the x-coordinate of the center to get negative 4, 0, and 4, 0. Note that the co-vertices are unlike the foci and the vertices, such that we add and subtract b units to the y-coordinate of the center. In this case, the distance b from the center to the co-vertex is 3 units, hence, we add and subtract 3 to the y-coordinate of the center. Thus, we have 0, 3, and 0, negative 3. The equation of this horizontal ellipse, in standard form, is x squared over a squared plus y squared over b squared equals 1. With a equals 5 and b equals 3, we substitute them to the equation and square them, so that the standard form of equation of this horizontal ellipse is x squared over 5 squared, or 25, plus y squared over 3 squared, or 9, equals 1. How about if we're given with the standard form of equation, and asked for the parts of the ellipse? This horizontal ellipse has a center at the origin, or 0, 0. A squared below x squared is 25, hence, the value of a is 5. With that, our vertices are at 5, 0, and negative 5, 0, or positive negative 5, 0. Next, b squared below y squared is 9, hence, the value of b is 3. With that, our co-vertices are at 0, 3, and 0, -3, are 0, positive -3. That would leave C, are the coordinates of the foci, missing. To solve for C, we will use the Pythagorean theorem, a squared equals b squared plus c squared. From the formula, we can solve for c squared by transposing a squared and b squared, so that we have c squared equals a squared minus b squared. Substituting a and b to the formula, c squared becomes 5 squared, or 25, minus 3 squared, or 9, equals 16. Hence, our c is 4, and our foci have coordinates 4, 0, and -4, 0, or positive -4, 0. Now, what about the standard form of equation of the vertical ellipse? Notice what changed at the standard form of equation of a vertical ellipse, especially at the denominator, a squared. It is below y squared. That would only be logical, since the major axis is now vertical. Thus, we will know from the standard form of equation if the ellipse is vertical or horizontal. If the bigger denominator is below x squared, then it is horizontal ellipse. And if the bigger denominator is at y squared, then the ellipse is vertical. This, on the other hand, is the equation of an ellipse, if its center is at hk. Say for an example, an ellipse whose distance from center to the vertex above is 9 units, so from the center, 2, 3, we add and subtract 9 to the y-coordinate, to get the coordinates of the vertices, 2, 12, and 2, -6. If the co-vertices are both 7 units away from the center, 2, 3, then we add and subtract 7 to the x-coordinate of the center. Hence, we have -5, 3, and 9, 3. Lastly, for foci, of course we have to add and subtract to the y-coordinate of the center, since they're the same with the vertices because they are collinear, but how much will we add and subtract? We can solve for c, using the Pythagorean theorem. From a squared equals b squared plus c squared, we can transpose the equation so that our c squared is equal to a squared minus b squared. Substituting the values of a equals 9 and b equals 7, we have 81 minus 49. Therefore, c squared is equal to 32, and c is equal to square root of 32 or 4 square root of 2. Thus, the coordinates of the foci are 2, 3 plus 4 square root of 2, are approximately 8.66, and 2, 3 minus 4 square root of 2, are approximately -2.66. In finding the standard form of equation of this ellipse, we can just substitute the value of a and b in the equation, and the center, h and k. Like in this given, the equation would be x minus 2 squared over 7 squared are 49 plus y minus 3 squared over 9 squared are 81 equals 1. Now, let's try solving some sample exercises related to ellipse. You can try to pause first the video to try these yourself, and then continue, once you're done, to check your understanding. So for the first problem, we are asked to solve for the equation of an ellipse, with center at the origin, one focus, at 3, 0, and a vertex, at -4, 0. It's given that the center is at 0, 0. Since the focus is at 3, 0, which is plotted along the x-axis, and the vertex is at -4, 0, which is also on the x-axis, we can say that the ellipse is horizontal, with c equals 3, so the foci is at 3, 0, and -3, 0. With one vertex given at -4, 0, we can say that the vertices are 4 units away from the center. Therefore, A equals 4, and the coordinates of the vertices are 4, 0, and -4, 0. What's missing as the value of B are the distance from center to the co-vertex. Since we already have the value for A and C, then we can just use Pythagorean theorem to solve for B. So B squared equals A squared minus C squared. Substitute A equals 4 and C equals 4. We will have B squared is equal to 4 squared, or 16, minus 3 squared, or 9, which is 7. Hence, B squared is 7. B therefore is square root of 7, and the co-vertices are 0, square root of 7, and 0, negative square root of 7. Substituting A and B to the standard form of equation, we have x squared over 4 squared, or 16, plus y squared over square root of 7 squared, or 7, equals 1. Again, that's x squared over 16 plus y squared over 7 equals 1. Did you get this answer correctly? Now let's proceed to the second given. In here, we are asked to find the center, foci, vertices, and co-vertices, given an equation of ellipse, in general form. So we have to rewrite it, in standard form of equation, by completing the square. Arrange the equation so that terms with x squared and x are grouped together, while terms y squared and y are also grouped. The constant is already at the right side of the equation, so this one's good now. Before forming our perfect square trinomials, factor out the coefficient of x squared, which is 9, so that we have 9 times x squared minus 14x. Do this for the coefficient of y squared as well, which is 16, so that we have 16 times y squared plus 4y equals 71. Do completing the square on x squared minus 14x by dividing 14 by 2, which is 7, and squaring it, which is 49. Add 49 after 14x, and add 9 times 49 on the right side of equation. This is because, by distributive property, what we added on the left was also 9 times 49. Next, perform completing the square on y squared plus 4y also. Divide 4 by 2, which is 2, then square it to get 4. Add 4 after 4y, and add 16 times 4 on the right side of the equation as well. Now we can rewrite this perfect square trinomial to square of binomial. We have 9 times x minus 7 squared, while the other perfect square trinomial becomes 16 times y plus 2 squared. Then, simplify the right side of the equation, it becomes 71 plus 441 plus 64. Or, that would be 576. Now to make our equation equal to 1, since that's how our standard form of equation of ellipse must be, we divide all the terms by 576. We simplify 9 over 576, as they are both divisible by 9. 9 divided 9 is 1, and 576 divided by 9 is 64. We also simplify 16 over 576 by 16. So 16 divided by 16 is 1, and 576 divided by 16 is 36. Lastly, 576 over 576 is 1. Therefore, our standard form of equation for this ellipse would be x minus 7 squared over 64 plus y plus 2 squared over 36 equals 1. From here, we can determine the coordinates of the parts of the ellipse. The center would be 7, negative 2. That's from x minus 7, and y plus 2, those are our h and k. We can say that this ellipse is horizontal because the higher denominator is found below variable x. Therefore, a squared is equal to 64, and a would be 8. We will add and subtract 8 to the x-coordinate of our center to get the coordinates of the vertices. Thus, our vertices are at 15, negative 2, and negative 1, negative 2. As for b squared, which is 36, b will be equal to 6. We add and subtract that to the y-coordinate of the center, so our covertices are at 7, 4, and 7, negative 8. Now to find c, and the coordinates of the foci, we will use Pythagorean theorem. So from a squared equals b squared plus c squared, to get c squared, we have a squared minus b squared. Substituting the values of a and b with 8 and 6, respectively, we have 8 squared minus 6 squared are 64 minus 36. Hence, c squared is equal to 28, and c is equal to square root of 28, are 2 square root of 7. To get the coordinates of the foci, we will add and subtract 2 square root of 7 to the x-coordinate of the center, just like in vertices. So our foci are at 7 plus 2 square root of 7, negative 2, and 7 minus 2 square root of 7, negative 2. Thank you again for watching. Hope you learned something from this video. If you do, kindly give us a like, subscribe, and hit the notification bell to get more lessons in mathematics for senior high.